Hello there, Mr. Sutton here with the AB Calculus 5.8 homework solutions on FTC derivatives of integrals.
For number 1, we're given x greater than 1 and we're told that f of x is the integral from 1 to x of 1 over t. We just want to find f prime. So using our fundamental theorem, since we're taking the derivative of an integral with x as the upper limit, we can essentially just take the integrand and replace the t with an x. So this is just going to be 1 over x then, which is going to be choice B. For number 2, we're given big F of x equals the integral from 0 to x of square root of t cubed plus 1, and we want to find big F prime of 2. So using our fundamental theorem, big F prime of x on this one, since we just have x here, is just going to be the square root of x cubed plus 1. I mean, we have an invisible tail of times 1, but we don't need to write it. But now we want to plug 2 into this. So that's going to be the square root of 9, which is 3. Choice D. For number 3, we want to know which of the following is an equation for the line tangent to the graph of y equals 3 minus this craziness at the point where x equals negative 1. So if we want tangent lines, remember we need 3 things. We need an x value, which they gave us. We need a y value, which we'll find in a couple moments. And we also need the slope at that x value. So to find the slope, we need to take the derivative of this y equals equation here. So that's going to be, let's see, 3 goes away because it's a constant. So we end up with then derivative of this integral from negative 1 to x of e to the negative t cubed. Since we're taking the derivative of an integral with an x as the upper limit, using our fundamental theorem, we can just replace the variable in the integrand with the x. So this is going to come out to negative, because we have a negative out in front, negative e to the negative x cubed. And then if we want to actually find the slope at x equals negative 1, we have to plug negative 1 into this function, into this derivative. So if we do that, let's see, negative 1 cubed is still negative 1 times a negative is positive 1. So this really all just comes out to negative e. Okay, well, that's our slope. Looking at our answer choices, there is only one answer choice, choice B, that has a slope of negative e. So if you were in a rush, you could pick choice B and move on. But if you're really curious about the y value, let's go ahead and plug in negative 1 to find the y value. So if we plug negative 1 into the function, we've got 3 minus the integral from negative 1 to negative 1 of all this stuff. Now, if you have an integral with the same limits of integration on the top and the bottom, that's an empty integral essentially. You're taking a base of 0, so you're going to have 0 area under that curve. This is just 3 minus 0 then, or 3. So we'd have y minus 3 equals negative e times x plus 1, which again gives us choice B. For number 4, g is a function whose first derivative is given by integral from 0 to x of e to the negative t squared. Which of the following has to be true on the interval from 0 to 2? And we've got choices such as g is increasing, decreasing, concave up, concave down. So we have to basically figure out whether g prime and g double prime are positive or negative to figure out which one of these choices to choose. Well, let's start with g double prime. That's the derivative of all this stuff. If we're taking the derivative of an integral that has x as the upper limit, FTC, fundamental theorem, says we can just plug the x in for the t here. We'd have an invisible tail of 1. We don't really have to worry about here. So g double prime then is just going to be e to the negative x squared. And now just revisiting g prime, that's going to be the area under this function. So are these positive or negative quantities? Let's take a look at e to the negative x squared. Because if we can figure out what this is doing, talking about the area is going to be a little bit easier. E to the negative x squared is a decaying exponential function. That means we're starting above the x-axis and approaching but never quite getting to the x-axis, because you can never really zero this thing out. So this is always going to be a positive quantity for all x values. So if this is positive, that means then that g double prime is positive everywhere. And if this quantity is positive, that means the area under it, g prime, also has to always be positive. So these things are both positive. Since g prime is positive, that means that the function is increasing. G double prime's positivity means that we're concave up. Increasing concave up, that's answer choice A. number 5, f is defined as the integral from 0 to x of this cubic function. We want to know on which interval is the graph of f concave down. So if we're talking about concavity, that means we need the second derivative. First derivative of all this, if we take the derivative of an integral with an x in the upper limit, we're just essentially replacing all the t's with x's, and we would multiply by the derivative of x, but that's just 1. So this is going to be 2x cubed minus 15x squared plus 36x. That's the first derivative. Second derivative will be 6x squared minus 30x plus 36. This is what we have to basically zero out, find the critical values for, and do some sign analysis on. All right, well, if I set this equal to 0, I can factor out a 6. That leaves me with x squared minus 5x plus 6. And just factoring this, that's going to be x minus 2 and x minus 3, which gives me critical values at 2 and 3. We're going to do some sign analysis for f double prime now. Those are our zeros that we're testing around. If I test a number less than 2, such as 0, plugging that in over here in the factored version, that's a negative times a negative is a positive. And now a number between 2 and 3, like 2.5, that's going to give me a positive rather, times a negative, comes out negative. And then a number bigger than 3, let's test out 4. So that's positive, positive, comes out positive. Now if we want to know where this is concave down, we're looking for where the concavity or the f double prime comes out negative. So that would be on the interval from 2 to 3, which gives us answer choice D. For number 6, f is given by the integral from 4 to 2x of the square root of t squared minus t. We want to find f prime of 2. Let's start by finding f prime of x. We're basically taking the derivative of this integral. Now, since I've got a variable in the upper limit, I can use my fundamental theorem, but when I do it, I can't just plug 2x in for t, although that's part of it. I also need to multiply by the tail, the derivative of 2x, which is 2. So this will come out to the square root of quantity 2x squared minus 2x times that tail of 2. And you can bet there's going to be an answer choice that incorporates forgetting this tail. All right, so this is my derivative. I'm going to simplify this just a little bit. This will be square root of 4x squared minus 2x with a 2 on the outside. Plugging in 2 now to get f prime of 2. Got to start on the inside and work my way out. So this will be 4 times 4 is 16, minus 4 is 12, so 2 radical 12. And look at my answer choices. They're not going to make me simplify the radical any more than that. We can choose answer choice E here. For number 7, we're trying to find the derivative of the integral from 1 to radical x of 1 over 1 plus t squared. So because we have a variable in the upper limit and we're taking a derivative of an integral with this situation, we can essentially just plug in this radical x wherever we see a t. There's a price though. We've got to use our chain rule and multiply by the derivative of radical x as well. So this will be 1 over 1 plus radical x squared times x to the negative 1/2, or 1 over 2 times x. All right, so we got to simplify this a little bit because none of the answer choices have this exact stuff in them. So we can definitely square this radical and get 1 plus x. And then we can multiply that by 2 radical x. So 2 radical x times 1 plus x, that's going to be answer choice A.
On this problem, we have the functions f and g differentiable and strictly increasing with a bunch of values for f and g in this table. And we've also got this weird h function that we don't end up using in the problem. This was one of many parts of a multi-part problem here that I got this from. So we've got w is a function given by the integral from 1 to g of x of f of t dt. Based off of this, we want to find w prime of 3. Well, let's start by finding w prime of x. Since I'm taking the derivative of an integral with essentially a variable or a function up here, I'm just going to replace this t in here with g of x. But when I do that, since g of x is its own function, I also have to multiply by g prime. So w prime of x then can be called f of g of x times g prime of x. This is just using our fundamental theorem of calculus. All right, so now I'm trying to figure out w prime of 3. So I'm doing f of g of 3 times g prime of 3. Well, g of 3, which we have to do before we can do f of g of 3, g of 3 in this table here is going to be 4. So this is really f of 4. And over here, g prime of 3 is going to be 2. So we have f of 4 times 2, and f of 4, it looks like, is negative 1. So negative 1 times 2 comes out to negative 2. On this problem, I'm trying to find the limit as h approaches 0 of this crazy-looking integral function over h. So I'm going to take the limits of these two things separately. If I take the limit of that integral function here as h approaches 0, I've got 1 plus 0. So essentially, I'm going from 1 to 1. An empty integral is just going to have a value of 0. Now, that's the same thing I would get as if I took the limit as h approaches 0 of just h, the denominator. Since these things both come out to 0, that means that I can use L'Hopital's rule. So I'm just going to take the derivatives of the numerator and denominator. Taking the derivative of the numerator, so setting up my limit as h approaches 0, my two derivatives here, derivative of the numerator. Well, since I'm taking the derivative of an integral with a variable in the upper limit here, I can essentially just replace the x here, the dummy variable, with this upper limit. So I've got the square root of parentheses 1 plus h to the 5th plus 8. And I would multiply by the tail of 1 plus h, but the derivative of this little expression here is just 1, so there isn't really anything to multiply by. Now doing the denominator, derivative of h with respect to h, that's just going to be 1. And so now I don't have an indeterminate form anymore. If I plug 0 in here, I've got the square root of essentially 1 plus 8, square root of 9, which gives me 3. Choice C.
For this calculator-based problem, we're given the f function here, which is an integral-based function. It's the integral from 1/3 to x of cosine of 1 over t squared dt, and it's on this interval from 1/3 to 1. We want to know at which of the following values does f attain a relative max. So if we want to figure out where f has a relative max, we need to know where f prime is changing from positive to negative. Well, what is f prime? F prime is the derivative of all this integral stuff. Now, since we're taking the derivative of an integral with an upper limit of x, we essentially are just plugging in this upper limit for the variable here, the t squared. And there's no real chain rule here because x, the derivative of x, is just 1. So this is just going to be cosine of 1 over x squared. That's it for that f prime. But now we need to figure out where this changes from positive to negative. So to do that, we're going to graph that out on Desmos. And let me just get the whole function in here. So I'll just call it the g function. We'll say g of x equals cosine, parentheses, fraction 1 over x squared. And we'll close that. And that's kind of a mess. Let's change the window from 1/3 to 1, because that's what they said we should be looking in. So we'll do, let's see, for the x-axis, 1/3 and 1. And I'll make my steps go by 1/3 so that I can see things a little bit easier. All right, so this is my function. And taking a look at where this is changing positive to negative, that happens right here at this 0.461 spot. So since we're changing positive to negative at x equals approximately 0.461, that means that f has a relative max at that x value. So that's going to be choice D.
On this problem, g is a continuously differentiable function, and we've got function values for g of 1 and g prime of 1. We're trying to find the limit as x approaches 1 of this crazy expression. So I'm going to take the limits of the numerator and denominator and see what we get. For the numerator, if you take that limit, you're essentially plugging 1 into that upper limit of integration. If you have an integral from 1 to 1, you have an empty integral with an area of 0. And now for the denominator, we would love to just say, g of 1 minus 6, but we have to be careful here because they didn't really tell us a whole lot about the g function. They did, however, say that g was continuous. They said continuously differentiable. that means that both the derivative and therefore the original function are continuous. So since g is continuous, why do we care? That means that the function value at all x values and the limit at all x values matches up. So this means that when I try to take the limit as x approaches 1 of g of x, I'm really just doing g of 1. So I can treat this whole denominator as essentially g of 1 minus 6, which is to say 6 minus 6, which is to say 0. So that was an awful lot of work, but we got 0 and 0 in the numerator and denominator. That means that we can use L'Hopital's rule. So we're going to take the derivatives now of the numerator and denominator. So taking our limit as x approaches 1 of the derivative quotient here, derivative of the numerator, since we're taking the derivative of an integral with a variable in the upper limit, we can essentially just replace the dummy variable with the upper limit. So this is just going to be g of x. And then for the denominator, we're going to have g prime of x, and then the 6 is going away because it's a constant. And now we're just doing limit as x approaches 1 of all this. Now, since this function is continuous and its derivative is also continuous, that means that taking the limit as x approaches 1 of these things is equivalent to just plugging 1 into these functions. Again, the function value and the limit match up because we have this continuity. So we're just doing g of 1 over g prime of 1. Well, g of 1 is 6, g prime of 1 is 3, so that gives us 2, which is answer choice D.
For number 12, we've got big F equaling the integral of 4 to x squared of square root of t, and we just want to find f prime of x. So for this one, we're just going to use our fundamental theorem. Since I have variable in the upper limit of integration, I'm just going to replace t with that stuff. But since this isn't just x, we're going to have to actually use the chain rule here. Multiply by the derivative of x squared, which is 2x. So we've got the square root of x squared times 2x. And I can simplify that. This is just x times 2x, which is 2x squared. Choice D. On number 13, we have h defined as the integral from pi over 4 to x of sine squared of t. Which of the following is an equation for the line tangent to the graph of h at the point where x equals pi over 4? So if I'm asking for a tangent line equation, I need an x value, which we have, a y value, which we can get by plugging this in up here, which we'll do a little bit later, and we also need a slope. So for the slope, we're going to have to take the derivative of h. Since this is an integral of the x in the upper limit, we can just use our fundamental theorem and replace the t with an x and get rid of the integral. So this is just going to be f prime equaling sine squared of x. Next, and this is actually h prime. Let's use the correct function name here. Next, we have to plug in pi over 4 for the x value. We want to know what the slope is at pi over 4. So we've got sine of pi over 4. That happens first. That's root 2 over 2. And then we're squaring that. So that's going to be, let's see, 2 over 4, which is 1/2. Next, so let's see, that narrows it down to, actually, hold on a sec. There is only one answer choice with a slope of 1/2. And that is going to be choice D. But before we go ahead and pick that, if you have time, not a bad idea, just to plug x in and see what the y value is. So if I plug x in, pi over 4 to the original function, I've got the integral from pi over 4 to itself of, well, we don't care, because if these limits are the same, empty integral is just going to give you 0. So putting it all together then, we've got y minus 0 equals 1/2 times x minus pi over 4. And that is equivalent, as we expected, to choice D.